Begin actually. So first, hi everyone, and welcome to the third talk actually of the third chapter of the PAC-Bayes seminar series. So just as usual, the reminder of the links to the website, the calendar, and there is a typo that should be fixed here. Sorry about that, and the link to the recorded seminars, which you can find on the website. Okay. As usual, there is some rules for question and answers. We're trying to be quite flexible about it also. So if you have questions, you can ask them in the chat, and then if there are breaks actually during the talk, probably you can we will select the questions actually and ask them to Yevgeny at that time. And are you okay with interruptions during the talk, Yevgeny,
Yes,
for
sure. You
questions, or
can
maybe
ask
just
during the talk. Yes, that's
okay,
fine.
perfect.
Mhm.
And just before we start, actually, I just want to remind that there will be three more talks after today's talk by Pascal Germain, Benjamin Gage, and Badreddin Sharif Abdelatif, actually. So you have here the titles of the talks and the dates, and you can find more details, including the abstracts, in the website, actually. That's all for the advertisement. So now I would like to introduce today's speaker, Professor Yevgeny Seldin from University of Copenhagen. So actually, you probably know his name already. Like Yevgeny worked on many things actually in machine learning theory, including like online and active learning, bandits, etc. But of course, he has also a huge number of publications related to PAC-Bayes bonds. And very important ideas actually, like studies of weighted majority votes, and super important paper on PAC-Bayes empirical Bernstein inequality, etc. But today, Yevgeny is going to talk about new work actually on recursive PAC-Bayes, which I think is a very important thing actually for this seminar series, because it's probably a different view and filling a gap actually between some aspects of temporal consistency in Bayesian analysis that might be a little different in the basic version of PAC-Bayes. So I'm quite excited about it. And then actually, Evgeny, the floor is yours.
So the plan for the talk today, I will, just start with a general background on generalization guarantees and so on, because, well, this is a post-Bayes seminar, and by teaching PAC-Bayes a lot, I can also see that people coming from the Bayes background see it maybe a little bit differently. So I will try to connect these two things. Then usually before I talk about PAC-Bayes, I talk about Occam's razor, which I call the little brother of PAC-Bayes, but we don't have enough time for it today. So I'm going to skip this topic, but I will show you where you can read about it. And that's like the first step if you would like to get into PAC-Bayes. And then I will actually talk a little bit more about PAC-Bayesian analysis. I saw that you managed to get half through several talks without actually seeing much of the proofs. So I'll show you a bit of the proofs, and then I will discuss the distinctions between PAC-Bayesian analysis and Bayesian learning. So the main idea is to reach this point where we can actually connect between PAC-Bayesian analysis and Bayesian learning and see where they are similar and where they are actually different. And then I will talk about the main topic of today, the recursive PAC-Bayes, the sequential update of priors within the frequentist learning framework. And maybe actually I don't expect that we reach majority votes, but I have the slides so you can see the slides later, and I will also show you where you can read more about this. And if you have any questions, feel free to interrupt me and ask the questions. I can also see the chat right here, so we can move with it forward. So we are in the usual supervised learning setting where we have a sample that's given to the algorithm. The algorithm spits out a prediction rule, and this prediction rule is used to make predictions on new data points. And, for example, you have a sample of patients that are labeled as sick and healthy based on the pulse rate and temperature. And then, you can find a classifier that says everything on one side of the hyperplane is positive, everything on the negative side is negative. And you can use it to classify new points. So the general supervised learning setting, I expect everyone is familiar with it. And yeah, so a bit of notation. So X is the sample space. Let's say in this case, the two-dimensional space. Y is the space of labels. If we're doing classification, it's plus or minus 1. If we're doing regression, real numbers or anything else you can think of. A sample is a labeled sample, a sample of pairs of X and Y's. And we have prediction rules denoted by small h that are functions from the sample space to the label space. And we use the big H to denote the set of prediction rules. Okay. Yep. So moving on. Now the important thing is the loss function. So the loss function, also called error function or risk function, that's the loss for predicting y prime when the reality is y, and there are many different examples of loss functions. So the 0, 1 loss, squared loss, absolute loss, and again, whatever you can think about. And the loss function determines the cost of different mistakes. So it tells us how much we care about one type of mistakes or the other type of mistakes. And so one example, if we are designing a fire alarm, and we have the prediction whether there is fire or no fire, and we have the reality of no fire or fire. If there is correct prediction, well, there is zero loss for that. But if the predictor says that there is fire and in reality there is no fire, well, maybe we call the fire brigade and pay 2,000 euro for calling the fire brigade. If the predictor says that there is no fire, but there is actually fire, then the whole house burns and we may lose the value of the house, let's say 5 million euro, okay? The point is that the cost of the false positive is sort of constant. That's the cost of calling the fire brigade. The cost of the false negative depends on the value of the house, meaning that different people may have different loss function, and based on that, they may calibrate their decisions differently, depending on how they care about different errors. And we'll get back to the importance of the loss function a bit later. Now, the quantity of interest that we are going to look at, that's the expected loss. So the expected loss or risk, that's the expectation with respect to the sample according to some distribution of the loss function. And once we write it, there is an assumption that x and y are actually sampled from some fixed but unknown distribution, p of x, y, just in order to be able to write this expectation. Now, the challenge is that the true distribution of x and y is unknown. If it would have been known, we would not need do any learning. So so we don't know what's actually the expected loss of any prediction rule that we have. So what can we say about the expected loss of a prediction rule? Well, we can look at the empirical loss of that prediction rule on a sample and use the empirical loss as an estimate. But this empirical loss is typically an underestimate of, so let's say in this case, we have perfect separation of positive and negative points, but probably we don't expect that the loss is going to be zero on all future samples, okay? So the key question is how close is the empirical loss to the expected loss? And this is the main question that we're going to study. And the typical way of approaching this problem is to do validation. So we split the sample into trained validation set. We use the trained sample to compute a prediction rule, and then we estimate the empirical loss of this prediction rule on the samples in the validation set. So we compute the average loss on the validation set. And if we stay with the assumptions that the samples in the validation set are independent, identically distributed, and they come from the same distribution as potential new samples, then we get that the empirical loss on the validation set is an unbiased estimate of the expected loss of our prediction rule. So if we just write the expectation of the empirical loss and we write down the definition of the empirical loss, we can take the expectation inside, and since the samples in the validation set come up from the same distribution as the new samples, we get that this is an unbiased estimate of the true loss. And the reason is that from the perspective of this prediction rule, the samples in the validation set are indistinguishable from any potential new samples that may come later. So if we take any sample in the validation set and we exchange it with a new sample, from the perspective of this prediction rule that was trained on the training set, nothing has changed. So in expectation, we have an unbiased estimate of the loss. Now, what can we say about the expected loss based on the empirical estimate of the loss on the validation set? Well, we know that it's an unbiased estimate of the loss, but if we consider the case that we have just one sample and we have the 0, 1 loss, the empirical loss is going to be either 0 or 1. So it's an unbiased estimate, but it's never close to the true loss, unless the true loss is 0 or 1. Which says us that, being unbiased is neither sufficient nor, as we will see later, necessary in order to be able to say something about the expected loss based on the empirical loss. So what we need concentration of the empirical loss around the true loss. And we are going to talk a lot about the concentration. So to formalize things, so if we take a random variable zi to be the loss of the prediction rule on sample xi and yi, and if the samples are independent, identically distributed, then we get a sequence of ID samples, and we are looking at the expectation of these random variables. And what we have at hand, we have an empirical estimate, so we have an empirical average of these random variables. And we're asking how far an empirical average of function evaluation on a set of data can be from the expected value of this function. So now we come to the first distinction between frequentist and Bayesian approaches to this problem. So in the Bayesian setting, in the Bayesian paradigm, the parameters of the data generating process are sampled from an unknown distribution. And Bayesian learning starts with the prior distribution on the parameters, and given the sample, it applies the Bayes rule and computes the posterior probability of different parameters generating the data. And the probabilities are over both the data and the parameters. So both the parameters and the data are random variables. And the loss function is actually not within the Bayesian formulation of the problem. So loss function is nowhere in the Bayes rule. In the frequentist paradigm, the parameters are, so this theta are unknown but fixed. And in the frequentist setting, we bound the probability that some loss function of the observations, like the empirical loss, deviates significantly from the expected value of this function, so the expected loss. And the random variable in the frequentist setting is the empirical loss, but not the expected loss. And all the probabilities that we're going to talk about will be the probabilities over the sample, but not over the parameters. Okay, so the PAC-Bayes analysis that we will discuss, it takes the frequentist path, and PAC in PAC-Bayes analysis stands for probably approximately correct learning framework, which is the frequentist learning framework, which will say that with high probability, that's a probably, the empirical loss that we will observe will be approximately equal to the expected loss. So this is the probably approximately correct learning framework. And one of the basic tools for studying concentration, that's Hovding's inequality. So in Hovding's inequality says that if we have a bunch of ID random variables in the 0-1 interval, then for any parameter epsilon larger than epsilon, the probability that the expected average of the random variables deviates from the empirical average of the random variables by more than epsilon is bounded by exponent of minus twice n epsilon squared. Or if we denote the right-hand side by delta, then epsilon equals square root of log of 1 over delta over 2n. So the probability that it deviates by more than square root of log of 1 over delta over 2n is bounded by delta. And therefore, if we take a loss function bounded in the 0-1 interval, and now it's important that the loss function is bounded in the 0-1 interval, and this is a kind of assumption that we don't always see in Bayesian learning. So in Bayesian learning, the loss function is not even explicitly there. And if we assume that we have a single prediction rule, h, that's independent of the sample, then for any parameter delta, the probability that the expected loss exceeds the empirical loss by more than the square root is bounded by delta, or equivalently with probability at least 1 minus delta, the expected loss is bounded by the empirical loss plus the square root. And the important point is that the probability is over the empirical loss, but not over the expected loss. The expected loss is unknown but fixed, and the random variable in this probability statement is the sample. Okay? Good. Now, in reality, we don't want just a single prediction rule. We want to select out of a set of prediction rules. So we can take a set of prediction rules, H, and evaluate each prediction rule on a sample. We get different empirical losses, and we can select the best prediction rule, the prediction rule that achieves the minimal empirical loss on the sample that we are working with. Now, the point is that if we now take this empirically best prediction rule and we look at the expected loss of the prediction rule that has achieved the lowest empirical error, the expected loss of this empirically best prediction rule, so the expectation now, this is actually a random variable, so we have to take expectation with respect to the sample, but the expected empirical loss is now not equal to the expected loss of this prediction rule on a new sample, because if we take any sample in the validation set and exchange it with a new sample, we may end up with a different minimizer. So now this minimizer, it depends on the sample, and since we have looked for the minimum of the empirical loss, this empirical rule that was selected, it's tailored for the sample that was used for its selection. So now the empirical loss is not an unbiased estimate of the loss on new samples. So so probably everyone has already seen this. But if not, then this is one of the most crucial parts of why we have to be careful when we are doing selection. And so maybe as an example, so let's say you take a coin and you flip a coin 100 times, but then you repeat this experiment several times. Even though in each experiment individually you have an unbiased estimate of the bias of the coin, once you select an experiment based, for example, the minimum of the bias of the coin out of all the experiments, you start underestimating. And this is the same effect happening when we start doing selection in learning. So the expected loss of the selected rule on new samples is not equal to the expectation of the empirical loss of this selected rule on what has been selected, because selection introduced bias. And as a result, we cannot apply Hovding's inequality because the expected loss is not, we cannot apply Hovding's inequality to the difference between the expected loss of this selected rule and the empirical loss. So what can we do in this case? The simplest approach. So if we have finite selection, we have a finite set of prediction rules. And again, we are doing this selection, so we evaluate the loss of all the prediction rules on a set of data, and we select the best prediction rule. And now we want to know what's the expected loss of this prediction rule. And this is our main tool for now, this Hovding's inequality. And we looked at the probability that the expected loss of the selected prediction rule exceeds the empirical loss by more than a parameter epsilon. And the expected loss of this selected prediction rule is not the expectation with respect to the sample of the empirical loss of the selected prediction rule. So we cannot apply Hovding. Instead, we bound this by the probability that there exists any prediction rule in this set for which the expected loss exceeds the empirical loss by more than epsilon. So we break the dependence. And then we apply union bound. So it's bounded by the probability, sum of the probabilities over the prediction rules that this is violated for any prediction rule. And now we can apply Hovding's inequality to this quantity. So we get the exponent of negative 2n epsilon squared. And we have m prediction rules. So m is the amount of selection that we are doing. And this is the concentration that we have for each prediction rule individually. And if we want to denote this right-hand side by delta, and we solve for epsilon, this gives us epsilon. And we get that the probability that the expected loss exceeds the empirical loss by more than the square root is bounded by delta. And m here, this is the cost of doing the selection out of n prediction rules. Okay. Now, if we move forward with this, we have the, oops, sorry. The slides are a little bit slow. Okay, so we have the approximation, estimation, and bias variance trade-off. If we look at the error, and let's say we want to select from a small set of prediction rules or a large set of prediction rules. And there is some optimal function that achieves the smallest loss. And we have the best loss function within a small set of prediction rules and the best prediction function in a big, large set of prediction rules. So if we work with a small set of prediction rules, we likely may not have a very good prediction function. So this will be the approximation error or the bias, and it's going to be most likely larger for the small set of prediction rules and smaller for a large set of prediction rules. But the problem is that we don't observe the true loss of the prediction rule. We observe an empirical estimate, and the empirical estimate can be a bit larger, a bit smaller than the true loss. If we take an alternative prediction rule within the same set of prediction rules, we also don't observe the true loss, we observe an empirical estimate. And if it happens that the empirical estimate of the loss goes below the empirical estimate of the best prediction rule, we may select a suboptimal prediction rule. So we may get confused which of the prediction rules is the optimal one. And this gives us the estimation error or the variance. And well, we can control with high probability that these estimates are within the square root of the true values. And here we have the number of prediction rules for which we compute the confidence intervals. And if we take a larger set of prediction rules, we have more prediction rules, so we cannot control as tightly all of them as we do in a small set of prediction rules. So there are sort of more prediction rules we can get confused with. And the estimation error, the variance goes up. So in a small set of prediction rules, we may have a large approximation error, but small estimation error. As the set grows larger, the estimation error grows, but the approximation error goes down. Okay? And we have this principle that the more is not necessarily the better. So taking a large set of prediction rules is not necessarily going to bring better predictions, because we might just get confused which of the prediction rules is the best one in this set. And slides are again slow. Okay, so to summarize, if we have a finite set of prediction rules, the probability that there exists any prediction rule for which the empirical loss deviates from the true loss by more than the square root is bounded by the number of prediction rules times the power of the concentration for each of the prediction rules individually. And if the number of prediction rules is much smaller than the exponent of the number of points, we have the expected loss under control. So concentration is stronger than selection. And we have the approximation estimation trade-off. So the approximation error goes down as we increase the number of prediction rules, but the estimation error goes up, and our control sort of first improves, but then starts going worse. And the question is how to hit the sweet spot where the set of prediction rules is large enough to have good prediction rules, but not too large to still be able to identify which prediction rules are the good prediction rules. And the challenge is that we have to pick the set of prediction rules before we start working with the data. And the answer is that it depends on the data. Sometimes there is simple data where you can take a small set of prediction rules and already find a good prediction rule that fits the data. And sometimes you have a complex data, so you need a lot of prediction rules to find a prediction rule that works well for the data. And again, the challenge is that we have to pick the set of prediction rules before we start working with the data. So how can we let the data speak for itself? And the first tool for working with this is Occam's razor, which I call the little brother of PAC-Bayes. And Occam's razor allows adaptive selection from a countable set of prediction rules, and it also provides a gentle introduction to priors in the frequentist learning framework, but we don't have much time to talk about it, so you can read a draft of my book on machine learning, the science of selection under uncertainty, where I actually start with Occam's razor and explain it in a bit more details. But we are going to jump directly into PAC-Bayes and then also talk about distinctions between PAC-Bayes and Bayesian learning. So the idea of PAC-Bayesian analysis, so we have seen that selection leads to increased estimation error. So the larger is the set of prediction rules, the larger is the estimation error. And the idea of PAC-Bayesian analysis is to use randomized classifiers. So a randomized classifier is a classifier that instead of giving back a single classifier, you return a distribution over classifier. So you are not saying I'm going to work with this classifier, you are saying I'm going to select 50-50 between two different or more classifiers. And this randomized classification, so randomized selection of the classifiers, can be seen as active avoidance of selection. So you're not committing to a single classifier. You are saying, I'm going, maybe I'm going to use this one, maybe I'm going to use a different one. And this so selection was increasing the estimation error, but active avoidance of selection reduces the estimation error. And what we get is that so instead of committing to a particular classifier, we return distribution, we avoid commitment. And for example, if we have two classifiers that have the same empirical error, then there is no reason to select among them if they have the same empirical error. So instead of selecting one of them and paying the price of selection, we return a 50-50 distribution, so we are not selecting among them. Then we stay at the same level of approximation error, but we are we are reducing the estimation error, we are reducing the variance of the estimation. Okay? And this approach, it can be applied not only to countable sets of prediction rules as in Occam's razor, but it can be applied to uncountable sets of prediction rules. So any questions so far? So again, selection, this is what was causing challenges with estimating the error of different classifiers. And here we're going to avoid selection to improve the estimation error, okay? Not that we're going to avoid it altogether, but in cases where we don't need to select, we're not going to select. So what is a randomized classifier? So if we have a distribution on a set of prediction rules, a randomized classifier samples the prediction rule according to this row of H, then observes the sample, and then returns the prediction of H on the sample. So this is how randomized classifier works. And a row is called a randomized classifier or a Gibbs classifier. Okay. And well, this point is quite similar to Bayesian learning. So in Bayesian learning, you also have a distribution over classifiers, and you can sample a classifier according to this Bayes distribution. And then we have the expected error of the randomized classifier, which is the expectation with respect to the classifier, the rho according to rho of the expected loss of the classifier. And we have the empirical error, which is the expectation, again, with respect to the same distribution of the empirical loss of the classifier. Okay. And now we start with an interpretation-friendly PAC-Bayes bound. So you have already seen a few PAC-Bayes bounds in this seminar. This is one more. So the average expected loss when we do selection according to rho is bounded by the average empirical loss plus square root of the average empirical loss times the KL plus the KL over N. And if we want to pick a distribution that optimizes the trade-off, so if we want to pick a distribution that achieves the lowest expected loss of the randomized classifier, we need to optimize the trade-off between the empirical loss, the average empirical loss, and the KL. So these are the two main terms that we have here. We also have this log of 2 squared n over delta, but this is fixed. And these are two terms that depend on the choice of the posterior distribution. And if we want to minimize the empirical loss, we have to assign high weight to prediction rules that have low empirical loss. But at the same time, we need to stay close to the prior distribution we have started with in this KL sense. And in particular, so if we take posterior that's equal to the prior, then the KL is 0, the KL diversion between the posterior and the prior, and we essentially get almost no penalty, and it follows what I have said earlier. So if we make no selection, we're not paying the penalty of the estimation error. So no selection, no penalty. And this bound also shows fast rays that were mentioned in the previous talk also. So if the empirical loss happens to be small, then this term is small, and the distance between the empirical loss and the expected loss decreases at the rate of 1 over n rather than 1 over square root n. So this bound shows you that PAC-Bayes is able to achieve these fast convergence rates when the empirical loss happens to be small. And it's also, so let's say when you work with neural networks, you can often achieve zero empirical error, and it gives you this benefit of if you have achieved zero empirical error, you can also assign a bit higher weight to these prediction rules with zero empirical error. Okay. Good. Still waiting for the slide. If anyone has any questions, feel free to ask your questions. Okay, so how do we work with the PAC-Bayes bound? So to start with, we have to select a prior over prediction rule. So let's say we work with linear separators, and this would be a set of vectors W that define the separating hyperplane in 2 dimensions. And we can start with the Gaussian distribution on the space of these vectors W that define the separating hyperplane. Then we can select a posterior, and so let's say we select, so we can separate the data and say that, well, this W star is a hyperplane that defines a hyperplane that separates the data, and then, but we cannot select a delta distribution on that hyperplane because then the KL would explode. So we need to smooth the posterior distribution in order to keep the KL under control. So we take this W as, and then we take a normal distribution around this vector W star. So then we can easily calculate the KL divergence. The KL divergence between two normal distributions is the norm of W star. The calculation of the empirical loss is getting challenging, and well, it's somewhat close to the challenges that you have in computing the Bayes, the loss of the Bayes posterior. So if we project everything on one dimension, we say that, well, this is the vector W and this is a point X, then the probability that, and let's say it's positively with positive label, then the probability that W star that the sampled. So now we don't predict with W star. We sample a vector according to the normal distribution. And then the probability that it misclassifies the point is equivalent to the probability that we sample from the Gaussian distribution and we flip the direction of W relative to W star. So it would be the tail of the Gaussian distribution. And then if we then we have the trade-off. So if this vector W is longer, then the probability that it flips direction when we sample from the Gaussian distribution decreases. But the KL divergence between the posterior and the prior increases, and the other way around. So here you already see that, I mean, in general, you can't work with any kind of prior and any kind of posterior. You have to select a prior and posterior for which you will be able to compute the KL divergence. And well, then you also have the challenge of computing the empirical loss using the posterior that you had. If X and W are not aligned, we can project them on the same line and then do the same in the projected space. Any questions? Okay, so now I will show the PAC-Bayes KL inequality, which is the key inequality in PAC-Bayes analysis. And for that, we define the binary KL divergence between two Bernoulli distributions with biases P and Q. And binary KL divergence, so P and Q now, they are not distributions, so they are numbers in 0 and 1, but it's just a shorthand for the normal KL divergence between these two Bernoulli distributions. And well, this is the definition. So it's 1 minus P log 1 minus P over 1 minus Q plus the other thing. So it's just a shorthand for the KL divergence between two Bernoulli distributions, but P and Q here, they are numbers, they're not distributions. And then the PAC-Bayes KL inequality says that for any prior distribution pi on a set of prediction rules that is independent of the sample, the probability that this binary KL between the average empirical loss and the average expected loss exceeds this quantity is bounded by delta. And the interpretation from the inequality that I have shown earlier follows from this PAC-Bayes KL by refined Pinsker's relaxation of the KL. So the refined Pinsker's relaxation says that if the KL is bounded by epsilon, then Q is bounded by P plus square root of 2P epsilon plus 2 epsilon. So if this is bounded by the right-hand side, then we get the bound that we had, the interpretable bound that we had on one of the earlier slides. So this inequality is not very easy to sort of get much intuition about it. So if you want intuition, it's better to look at the interpretation-friendly version of it. Now, I will quickly show you a proof of this inequality. So the proof is based on Donsky-Bardhan's variation formula that you have already seen in the previous talk. So this is the formula, and if you look at the right-hand side, so then you have that for any random variable, the log of the expectation of the exponent is bound by the supremum of this. And it means that for any function, the average of the function minus the KL between the posterior and the prior is bounded by logarithm of the expectation of the exponent of the function. So this is the change of measure inequality that follows from the dual representation of the KL divergence. And then slides are a bit slow. And from this, we get the PAC-Bayes lemma. The PAC-Bayes lemma says that if we have a distribution pi that's independent of the sample, then the probability that there exists any distribution such that the average of the function exceeds the KL plus logarithm of expectation with respect to pi expectation with respect to the sample of the exponent of the function over delta is bounded by delta. Okay, and the proof is relatively short. So, well, this is the statement that we want to prove. And first we take the KL to the left side of the inequality, and we swap the expectation with respect to the sampling of the sample and expectation with respect to pi. So if pi is independent of the sample, we can swap these two expectations. So this is where independence of pi and s are important. And then we have the change of measure inequality. And well, this is essentially the left-hand side of the change of measure inequality. And we know that it's bounded by the logarithm of the expectation with respect to pi of the exponent of the function. So we just plug it here. And we have the same on the right-hand side. And then we apply Markov's inequality, and Markov's inequality says that if we have a random variable, the probability that the random variable exceeds expectation over delta is bounded by delta. This is our random variable, and the probability that it exceeds its expectation by more than 1 over delta multiplicative factor is bounded by delta. So this gives us the PAC-Bayes lemma. And now the important point is that change of measure inequality deterministically relates this left-hand side for all posterior distributions rho to a single quantity that only depends on the prior. And then the probabilistic argument that we had in this step was applied to a single quantity, this expectation with respect to pi of the exponent of the function. So this is the key point. So the change of measure inequality relates all posterior distributions to a single prior distribution pi, and then we have just a single probabilistic argument applied just to pi. And in this sense, the change of measure inequality acts as a replacement to the union bound that we had in the finite case. So the union bound we can only apply to finite sets of prediction rules. Therefore, union bound only works when we have finite or countable sets of prediction rules. Change of measure applies also in uncountable cases of uncountable sets of prediction rules. And well, this is the key to get generalization for uncountable sets of prediction rules. Questions? Okay. Let's move forward. So now I will also quickly show a proof, one slide proof of PAC-Bayes KL. So this is what we want to prove. This is the PAC-Bayes KL inequality, and this is the PAC-Bayes lemma that we have derived on the previous slide. And essentially, we just need to pick a function. So we pick n times the KL between the empirical loss and the expected loss. And there is a KL lemma that I will not show that shows that for any prediction rule, the expectation of the exponent of n times KL is bounded by 2 square root n. And then for the proof of PAC-Bayes KL, so this is what we want to prove. And first of all, we use convexity of KL to take expectation outside, and we also multiply both sides by n. And by the KL lemma, this expectation with respect to the sample of the exponent of n times KL is bounded by 2 square root n. This is what we have here. And then we just plug it into the PAC-Bayes lemma and we're done. So this is our function, n times KL, and the probability that the average of the function exceeds the KL plus logarithm of the expectation with respect to pi of the expectation with respect to the sample of the exponent of the function, and this is our function. So this thing is bounded by delta. So once we have the PAC-Bayes lemma and well, we have the KL lemma that bounds the exponent of this thing, then we immediately get the PAC-Bayes inequality. Okay. I know it may be fast. You can take later the slides and check them. And the same way, so this is the PAC-Bayes lemma. And different choices of this function f give different measures, different ways of measuring the distance between the empirical loss and the expected loss. So for example, in PAC-Bayes KL, we have taken this function and we use the KL lemma, but you can also use Hovding's lemma and get an inequality similar to what you have seen in Pierre's talk in the first lecture. Or you can use Bernstein's inequality, Bennett's inequality, unexpected Bernstein's inequality, or whatever. So you can combine all these techniques just by choosing a different function here and having a bound on the expectation of the exponent of that function, which you have in intermediate steps of the proofs of Bernstein's, Bennett, unexpected Bernstein, and so on. And then you get the different PAC-Bayes inequalities. So you get PAC-Bayes Bernstein, PAC-Bayes Bennett, PAC-Bayes unexpected Bernstein, and so on. And then different choices of posteriors and priors give different regularization measures. So for example, if you take Gaussian prior and Gaussian posterior, you get regularization by the norm of W. If you take Laplacian priors and Laplacian posteriors, you can get regularization by the L1 norm of W, and so on. And these two things, so you have orthogonally the choice of the function and the choice of prior posterior pair, and any of these can be combined together and plot together. So this is what I call the modularity of PAC-Bayes. Okay. And okay, I think I will skip minimization of the bound, but you can write this bound in a way that you can actually minimize it. The important point here that the minimizer of the bound usually takes the form of Gibbs distribution. So if you have a prior, so the posterior distribution takes the form of the prior times the exponent of negative n lambda, the empirical loss. And now we get to the differences between the PAC-Bayes and Bayesian learning that I have summarized on this slide. So in PAC-Bayesian bounds, the pi of h is an auxiliary construction in the proof. And the bound always holds. So we get a bound on any posterior distribution that holds for any choice of the prior that's just independent of the sample. In Bayesian learning, pi of h is a prior belief that this parameter was selected for generating the data. The PAC-Bayes provides a high probability guarantee on the distance between the expected empirical loss and the average empirical loss and the average expected loss, whereas the Bayes rule provides a way to update posterior prior belief to a posterior belief through the Bayes formula. And now the loss function is central element in PAC-Bayes, and it impacts the choice of the minimizer. So if you take a different loss function, you will get a different posterior distribution. Whereas in Bayesian formulation, the loss function is not part of the Bayes rule. The PAC-Bayes bounds hold for all the posterior distributions, whereas in Bayesian case, you have a posterior that is a conditional distribution, so it's also not exactly the same semantics of the posterior in the PAC-Bayes and Bayes. PAC-Bayes typically assumes that the loss is bounded in the 0-1 interval, or otherwise you need either to smooth the posterior distribution to make some assumptions that will ensure concentration of the empirical estimates around the true expected values. And bounding the loss in the 0-1 interval, that's one way of ensuring that the empirical estimates converge to the expected values. In Bayesian learning, it's not directly a concern whether the loss is bounded or unbounded. Now, if the loss is a negative log likelihood, we can write the posterior distribution as the exponent of negative n times the empirical loss. And then the posterior is, the probability, and then the posterior is proportional to the prior times the exponent of n times the empirical loss. In PAC-Bayes, the posterior is the Gibbs distribution, so it's proportional to the prior times the exponent of n, but then we have this parameter lambda, and parameter lambda is typically smaller than 1, so it's not exactly the same posterior. And if the loss is not the negative log likelihood, then the posterior has a different shape altogether. And then there is actually one more point. So it's often said that we can use PAC-Bayes to provide generalization guarantees for Bayesian posteriors, but actually there is this question of whether the loss is bounded or not bounded. And if the loss is unbounded, then we can't just plug Bayesian posterior into PAC-Bayesian bound. We either need to smooth the posterior or we need to make some assumptions that would ensure concentration. So it's not that you can always plug a Bayesian posterior into PAC-Bayes bound and get a guarantee, generalization guarantee. If the loss is not bounded, then it may require some additional work. It may be possible, but it requires additional work to get generalization. And then the last point is that Bayesian learning requires an explicit prior in order to make this update from the prior to the posterior. Whereas in PAC-Bayes, a bound on the KL is sufficient to work with the bound. And for example, we can use distribution-dependent priors. So distribution-dependent prior depends on the distribution of the data. So it doesn't depend on the sample. We have no access to it, but if we can bound the KL, we can still work with the bound. Okay. So this was a summary of the bounds. And now we get to the recursive PAC-Bayes and how we do sequential updates of the priors in the frequentist framework. So, one idea is where the priors in PAC-Bayes actually come from. Well, we can use some prior knowledge to construct a prior, but one possibility is to use part of the data to construct a data-informed prior, and the rest of the data to compute the bound. So if we have n data points, we can split it into part of the data to construct a prior, and then the rest of the data to compute the actual bound. Okay? Now, the advantage is that we get a good prior, that we get the prior that depends on part of the data. The disadvantage is that the denominator of the bound will depend on the number of data points that are used for constructing the bound, so it will be less than n. It will be this m. And then the challenge is that all the confidence information, so we have constructed the prior, but all the information about how much data were used to construct the prior, was the prior constructed in a single step or whether we did multiple steps. All this information is lost. So we just have the prior, and it doesn't matter whether we used a lot of data to construct the prior or little data, it's all treated the same way in the next step. And the particular multi-step processing is not very helpful because we are losing all this confidence information as we move forward. Okay? So this very basic procedure that we had in Bayesian learning, take the prior from the current processing step and turn it into the posterior for the next data processing step, becomes sort of loses the value when we move to the PAC-Bayes setting. So this is the challenge that we have addressed with the recursive PAC-Bayes. And the idea is quite simple. So the idea is to use recursive loss decomposition. So now we have a sequence of priors and posteriors. Therefore, I write it as pi t. So pi t is the posterior at time step t that's going to become the prior for time step t plus 1. So this is the quantity that we are interested in PAC-Bayesian analysis, and we write it as, well, this same quantity minus some parameter gamma t times the expected loss with respect to the prior plus gamma t, the expected loss with respect to the prior. So I just add and subtract this term. So this is essentially the recursive loss decomposition that's behind recursive PAC-Bayes. And the main observation here is that sort of this quantity is of the same type as this quantity. So we can continue and decompose this recursively and go on and on and on. Okay? So to make it a bit more explicit, I will make an illustration of decomposition into three terms. So we have our data that we split into S1, S2, and S3. We start with some pi0 that doesn't depend on the data. We will use S1 to construct pi1. We will use S2 to construct pi2, and we will use S3 to construct pi3. So we will sequentially construct this sequence of pi1, pi2, and pi3. Okay? And now we look at the final step. We looked at the average loss with respect to pi3. And we can apply this recursive decomposition. So it's the average loss with respect to pi3 minus the parameter gamma 3 times the expected loss with respect to pi2 plus gamma 3, the expected loss with respect to pi2, which is again decomposed recursively into expected loss with respect to pi2 minus expected loss with respect to pi1, and plus gamma 2, the expected loss with respect to pi1. So this is the recursive loss decomposition. Okay, I'll give you a moment more to look at it. And now what happens if we would have computed the PAC-Bayes bound on this directly, we should have used data that were not used for construction of pi3. So this is S3. So we could only use S3, the last chunk of the data, to compute a direct bound on this quantity. What happens with recursive decomposition is that, I mean, this is just, the average with respect to pi1, and pi1, so pi0 was not dependent on the data, so we can use, the scale between pi1 and pi0, and we can use all the data when we compute the bound on this term. For the next term, we can use S2 and S3 to compute the bound on this term, as we would have if we would have, just computed the bound on the expectation with respect to pi2 on L of H. And then for the last term, we can only use the last chunk. So you can already see that there is much more efficient use of the data than just, using the last chunk to for computing a direct bound. Okay. If you look at this a little bit closer, so in the early steps, we start with the poor prior. We don't know much about the data yet. So we will have large scale divergence between the posterior and the prior. So we will have a large, but on the other hand, we can use a lot of data. So we have a large denominator when we compute the bounds for the early terms. And we have this coefficient gamma 2 times gamma 3. And if you have more steps, you will have more coefficients. So you have very small coefficient that multiplies this early term. So you can afford having poor prior and large scale because it's not going to matter too much for the final bound. When we look at the late steps, by the time we reach evaluation of this term, we will have a good prior, so we will have a small KL divergence. And we will also, so this is an excess loss, which has generally smaller variance than the plane loss. So we will also, we can also benefit from small variance of the excess loss. So we get a double benefit. We have small KL divergence, and we can benefit from small variance. So we can get, quite tight bounds for this term as well. And then in general, waiting for the slide to switch. And then the general way, a good way to split the data is to use geometric split, meaning that you double the size, or you start with allocating half of the data for the last chunk and then half of what's left for the previous one and so on, because it leaves enough data to compute a good bound on the first term and uses little data. So you use little data to bring a prior to a good region. and then you still have enough data to compute a good bound for the last term. So geometric split works quite well empirically. And just, I think the next should be the result of how this works. Yeah, so if you do empirical, so there are some baselines of, just using uninformed priors, using informed priors, using, excess losses, and these are recursive decompositions into 2 terms, 4 terms, 6 terms, and 8 terms. And you can see quite dramatic improvement in both the test loss and the bound as we go from non-recursive approach to the recursive approach. So Occam's razor was skipped, but then we have shown the PAC-Bayes bound, and we have shown the recursive decomposition. I didn't have time to talk about majority votes, but an interesting open question, if you are looking for open questions, is to do recursive bounds for the weighted majority votes, and you will need, to check the slides or read about weighted majority votes in order to understand the question, but that's one big open question that we have. And then if you want to read more, then you can check the draft of my book. That's also in the slides where I do all these things slowly. Good. Thanks for your attention, and sorry for keeping you a bit over time. And if you have any questions, I'm happy to take the questions.
Well, my question was potentially very silly. I was just wondering whether there was some sort of necessary dependence between your data splitting scheme and your eventual choice of gamma, whether those two things were connected in some way, or otherwise what the intuition of how these gammas emerges.
That's a very good question. So generally, so far we have not experimented much with gamma. In the experiments that I have shown, we have just taken gamma equals 1/2, and it worked well. There is a lot of room to experiment and see what would work well or not. In general, so if you look at this decomposition, okay, sort of the point is that you want, in general, you expect that the loss with respect to the posterior will be smaller than the loss with respect to the prior. And to get the most benefit from the variance reduction, you want to get gamma that would guess how much reduction you expect, so that this would actually be equal to gamma times the average with respect to the posterior.
Mm.
And you could potentially even, and gamma has to be independent of the data on which you are computing, this term, but it can actually depend on past data, on everything that, happened before pi t minus 1. So you can potentially use early blocks to estimate gamma and then use that estimates to get better gammas for the later blocks.
Okay.
If it makes sense.
Terrific. Yeah, it makes perfect sense.
But,
Thanks so much.
But we didn't have much time to, before we, so for the submission, we only experimented with gamma equals 1/2. And that already gives quite a lot. So you can potentially play with it and get further improvements. Yes.
Thank you.
I have comment and question related to the recursive PAC-Bayes actually. First, I find the idea super nice because especially like there were many papers trying to get like empirical bounds, empirical PAC-Bayes bound actually on neural networks. And some of them actually use that in the sense implicitly by splitting the sample in two, learning, a prior on the first half and evaluating on the second half. But it seems to me like this is more principled actually in the sense that you see that there will be rigorous ways to do it and to actually use maybe just more than arbitrary one split, but many splits of the data. Now, I think that there is an interesting thing to remark in terms of, how could I frame that? Like the consistency of Bayes learning, actually. So when you're learning Bayes, if you use, as you mentioned, Yevgeny, like you have a big sample, but you can split it in two. You start from the prior, you update your knowledge based on the first sample, you obtain the posterior, and you reuse it as a prior to learn on the second part of the sample, actually. And as you say, like if you do it in PAC-Bayes, you will not have the same results. And if you do it in Bayes, actually, it's the same thing as learning directly from the prior and with the whole sample. I think that the remark, sorry, I'm taking too much time actually, but the remark I wanted to make is that if you take the PAC-Bayes bond, as is still written on your slide, actually in the middle, in the small loss regime, small risk regime, actually. So if you remove the square root, actually, imagine that the square root in the middle of the bound can be removed. Then you recover again this consistency, actually, in the sense that with the bound in just KL over N, then this bound actually is compatible in the sense that if you break the loss into, L1 and L2, actually, say the empirical risk, sorry, into L1 first part of the sample and L2 second part, then actually you would obtain the same posterior if you do everything on the same sample or if you break into parts and then do two successive updates. It's because of the square root that things are not compatible anymore, which makes this work interesting. But for me, it also raises a point, actually, a question. What breaks between the fast rate regime and the slow rate regime that breaks actually this kind of consistency of the Bayes update, actually? Sorry, I hope it makes sense.
So you mean in the Bayesian learning, whether you do it in one step or you make it in two steps, you get the same final result. That's
Yes.
you were saying.
And I'm saying in PAC-Bayes bound, if you remove the square root term, if the PAC-Bayes actually that is still on the side, if you remove the square root term, this becomes true too, actually. It is the square root, which is necessary when you have a high risk, but it is the square root actually that is breaking things, interestingly, actually.
That's an interesting observation, yeah. Yeah.
I don't know if it's more than a coincidence but in a sense, the Bayes rule update to work also usually requires to assume that the likelihood is correctly specified, etc., which you don't have in PAC-Bayes. So I was thinking maybe in a sense, but it's very hypothetical, maybe it's just the fact that Bayes learning is a little too optimistic, while actually PAC-Bayes has also this high-risk regime where suddenly things break, but you still have actually this recursive PAC-Bayes gives a way to still do something with this. So I don't know. I found it interesting anyway. Sorry if I'm a little confused. It's late here, so I'm not able to phrase things very well anymore.
Yeah. Again, the main point about this recursive PAC-Bayes was that when you have used some data to construct a prior, you already have some confidence information about it, and you want to keep it, and you are keeping it. But it's true that you're getting different outcomes if you do it in one step or in two steps. And actually, as you see from the experiment, so sort of doing it in multiple steps, at least empirically in most cases, gives you tighter bounds and tighter.
It's a very valuable intervention, I think.
Doing it in one step. And again, it's because you are using some data to bring the prior to a good region, and then you are sort of validating whether you are in a good region. Unlike if you do it in one step, then you start with the bad prior and you are looking in a very huge space of possibilities. So that's why you are getting not such a good bounds. Yeah.
Any other question? Okay, if not, on my side, I will go to bed because actually it's getting late here in Singapore. But thanks a lot, Yevgeny, for your nice talk. And don't worry, so there is no talk next week actually, but the next talk is in 2-3 weeks maybe actually, and Pascal Germain's talk. So looking forward to it. And until then, just take care. Thank you.
Thanks again for organizing and thanks for your attention. Bye.